Stage 1 of model-based inquiry is called planning for engagement with important science ideas. Unlike the other stages, this work happens before students ever enter the classroom. Stage 1 is where teachers do the intellectually rigorous planning that makes the rest of the unit possible. The decisions made here shape what students will investigate, what ideas they will work with, and how they will ultimately make sense of the anchoring phenomenon. In model-based inquiry, planning begins with the end in mind. Teachers are not simply assembling activities. Instead, they are planning backwards from the explanation they want students to be able to construct over time. The final summative assessment for an MBI unit is a final evidence-based explanation that students write individually in Stage 5. Knowing this from the outset shapes every planning decision in Stage 1. This means identifying the science ideas that are essential for explaining the phenomenon and thinking carefully about how students will encounter, test, and revise those ideas across the unit. Stage 1 establishes the learning targets that will guide instruction through all 5 stages of MBI. A key part of Stage 1 is unpacking the standards. The teachers identify the relevant disciplinary core ideas, along with the grade band progressions, to understand where students are coming from and where they are headed. The MBI planning template is designed with the next generation science standards in mind, particularly the emphasis on disciplinary core ideas, science practices, and cross-cutting concepts. At the same time, this approach is flexible and can be used with any set of science standards, as the core work involves identifying the central ideas students need to explain a phenomenon and how those ideas develop over time through science's practice. Rather than treating standards as a checklist, Stage 1 uses them as a resource for sense-making. They help teachers clarify which ideas are central, what is and isn't important about these ideas, how those ideas develop over time, and why they matter for explaining real-world phenomena. Another important part of Stage 1 is planning for equity and social justice. This section prompts teachers to think carefully not only about what they will teach, but also why and how they will teach it. The goal is to design units that are inclusive, relevant, and empowering, so that all students can engage meaningfully in science and see themselves as capable contributors. One key focus is centering students' community, cultural, and individual resources. This means building on the knowledge and experiences students bring with them and creating opportunities for those resources to play a role in classroom sense-making. This might involve connecting to local contexts, incorporating multiple ways of knowing, or designing opportunities for students to bring in perspectives from their own lives and communities. In some cases, teachers may also choose to connect science learning to social justice issues in ways that orient to socially just transformation. This can involve using science to investigate real-world problems that impact communities and considering possible actions or solutions. While this step is optional, it can deepen engagement by making clear how science can be used to understand and respond to issues that matter to students. Planning for equity and social justice is not something added on at the end. It is woven into the design of the unit from the beginning, shaping the phenomena we select, the questions we ask, and the opportunities students have to participate in meaningful ways. Stage 1 also involves selecting a scientifically rich, real-world anchoring phenomenon. In model-based inquiry, the phenomenon is not an example used to illustrate ideas after instruction, and it is not a motivational hook that students move past quickly. Instead, the phenomenon is the reason for the unit. A strong anchoring phenomenon raises a genuine explanatory problem for the students. It is something students can observe, wonder about, and return to repeatedly as their thinking develops over time. Importantly, it requires multiple science ideas to explain, and cannot be resolved with a single fact or definition. When selecting an anchoring phenomenon, teachers also consider whether it can support a meaningful driving question. A strong driving question presses students to explain how and why the phenomenon occurs and cannot be answered immediately or by looking up information. Instead, it is designed to be answered gradually through investigation, modeling, and evidence-based reasoning. A well-chosen anchoring phenomenon creates a need for students to engage in science practices across the unit. It motivates the investigations in Stage 3, the model revisions and consensus building in Stage 4, and the final explanation students write in Stage 5. In this way, the anchoring phenomenon serves as the conceptual through line or problem space that holds the entire MBI unit together. In the Hindenburg unit, the anchoring phenomenon is the rapid ignition and destruction of the German airship in 1937. The driving question asks how and why the airship burned so quickly. Explaining this event requires students to reason about chemical reactions, energy transfer, activation energy, and evidence from investigations of how energy is released. In the Lamsilis muscle unit, the anchoring phenomenon centers on how lifelike mantle lures evolved in freshwater mussels. The driving question presses students to explain how variation, mutation, and natural selection led to the evolution of these lures over time. In both cases, the phenomena were chosen because they are compelling, complex, and require students to work with multiple science ideas to develop a coherent explanation. Once the phenomenon and driving question are identified, teachers develop a target explanation and an example final model. These are planning tools for teachers, not products that students are expected to reproduce. The target explanation represents the kind of gapless, evidence-based explanation students should be able to construct by the end of the unit. It clarifies the key science ideas that must be coordinated and helps teachers distinguish between what students are expected to figure out through investigation and what ideas may need to be introduced or supported instructionally. The example final model serves a similar purpose, but in visual form. It provides a vision of what a student model might include after students have engaged in multiple rounds of investigation, model revision, and consensus building. Importantly, this model is not shown to students. Instead, it helps teachers anticipate how ideas could be represented and connected over time. In the Hindenburg unit, the target explanation coordinates ideas about hydrogen as a fuel, the mixing of reactants, activation energy, and energy transfer during exothermic reactions. In the Lamsilis muscle unit, the target explanation brings together ideas about variation, mutation, natural selection, and reproductive success across generations. Together, the target explanation and example final model help ensure that tasks, discussions, public records, and assessments are all aligned toward the same explanatory goal, while still leaving space for students to do the intellectual work of figuring out the phenomenon for themselves. Another critical part of Stage 1 is identifying the important science ideas that will anchor the unit. These ideas are surfaced in the target explanation as the high-leverage ideas needed to explain the anchoring phenomenon. Here, teachers identify a small set of core ideas, typically between 3 and 6, that are central to the target explanation and necessary for explaining the anchoring phenomenon. These ideas are not just topics to be covered. They are the key concepts students will need to work on, revisit, and refine as they make sense of the phenomenon. These important science ideas play a central role in shaping the unit. They guide the design and selection of tasks in Stage 3 as opportunities to foreground these ideas, helping ensure that each investigation provides students with opportunities to develop and use these ideas in meaningful ways. In this way, the important science ideas serve as a bridge between planning and instruction. They connect the target explanation developed in Stage 1 to the day-to-day work students will engage in as they build toward explaining the phenomenon. Stage 1 sets the foundation for everything that follows. The science ideas identified here shape the tasks in Stage 3, the model students build and revise, the public records that track learning, and the explanations students ultimately write. By investing in careful planning at the start, teachers create the conditions for students to engage deeply in sense-making throughout the unit. Planning for engagement with important science ideas ensures that model-based inquiry is coherent, purposeful, and intellectually rigorous. In the next stage, students encounter the phenomenon for the first time and begin sharing their own ideas about how it might be explained. To explore the MBI planning template and example units, visit modelbasedinquiry.com.